The Euler-Phi function, or totient, is one of the most important functions in all of mathematics. But how can we find the number of numbers relatively prime to n without finding the numbers relatively prime to n? Let's start with a few simple cases. So again, a common strategy in number theory is to start with the primes. Suppose n is prime. Since n is prime, then all numbers less than n are relatively prime to it. This means that if n is prime, phi of n is n minus 1. So we could find phi of 31. Since 31 is prime, phi of 31 is 31 minus 1, or 30. Now suppose n is p to the k, the power of a prime. So let's consider which of the numbers less than p to the k are relatively prime to p to the k. Now at this point we'll invoke something that's a useful strategy. Sometimes it's easier to solve a harder problem. So in this case, while we only want to find the numbers less than p to the k that are relatively prime to it, let's include p to the k itself. Now, since p is prime, the numbers not relatively prime to p are the multiples of p. Now, optics matter, and if we want to think about these as multiples of p, then this last one, p to the k, I want to think about that as something times p, and so I'll rewrite it. And the important thing about this is that we see there are p to the power k minus 1 multiples. So if we eliminate these numbers, which incidentally also eliminates p to the k, then we'll have p to the k numbers, and we'll subtract p to the k minus 1 numbers, and doing a little factoring, we'll find that we have p to the k minus 1 times p minus 1 numbers left. And so these are the numbers that are relatively prime to p, and that gives us our theorem. If n is a prime power, then phi of n has this form. For example, find phi of 32. And so we note that 32 is 2 to the 5th, a prime power. And so our formula tells us we have, now since 32 is 2 to the 5th, it will be relatively prime to all odd numbers less than 32. And so there are, well, let's try and count these. The idea is we'll take our numbers and we'll count them 1, 2, 3, 4, and so on. And we might note that the indices can be found by adding 1 and then dividing by 2. So 1 plus 1 is 2, divided by 1 is 1. And so the last index is 16, and so there's 16 numbers that are relatively prime to 32. What if n is p times q where both p and q are primes? Well, let's try it out. Remember, concrete doesn't hurt. Let's find phi of 15. So consistency counts. We want to find the numbers among 1 through 15 that are relatively prime to 15. That's 3 times 5. Now we can strike out all the numbers that have a factor of 3. There are 5 such numbers. Likewise, there are 3 numbers that have a factor of 5. And note that we struck out 15 twice, because there's one number that has a factor of both 3 and 5. So of our 15 numbers, we'll take out the 5 that have a factor of 3, the 3 that have a factor of 5, but then we'll add back in the one that has a factor of both, for a total of 8 numbers relatively prime to 15. So we can generalize from this. Suppose n is a product of primes where p and q are both prime. Of the numbers from 1 through n, p of them have a factor of q, q of them have a factor of p, and 1 has both. So phi of n is going to be pq, that's the number of numbers, minus those p that have a factor of q, minus those q that have a factor of p, and add back in the one we've struck out twice. So again, Optics matter. Now, since they're both prime, phi of p is p minus 1, phi of q is q minus 1, and notice these last terms, we could rewrite them as minus q minus 1. But if we take a look at these first two terms, they have a factor of p, and if we remove that, we get another q minus 1, and we'll write this as 1 times q minus 1 for consistency. And notice that we can factor q minus 1 out and get, which is phi of p times phi of q. And so that gives us our theorem. If p and q are prime, then phi of the product is the product of phi of p and phi of q. So if I want to find phi of 55, since 55 is 5 times 11 and both 5 and 11 are prime, then phi of 55 is phi of 5 times phi of 11, which is... What about a product of 3 primes? If n is a product of 3 primes, then we'd like to say, but we can't. The preceding theorem only holds if both factors are prime and the product QR isn't prime. So what can we do? We'll take a look at that next.